Well, thanks, Julie. Thanks for having me. I'm really excited to get to talk to y'all today. So, as Julie said, I'm Moriah Henning. I currently work with Turning Point Company. I used to be Energy Resources Integration, and we are a energy efficiency consulting company with Rocky Mountain Power. We take care of their resource extraction group, which is oil, gas, mining for Utah and Wyoming. And so just like you guys do, we go out to sites, look for ways that companies can reduce their energy. We focus on electrical energy since we are with Rocky Mountain Power. And a lot of what I do is working with pumps. So that's what I'm going to talk to you guys about today. Let me share my screen really quick. And as Julie said, I am an alumni of the U and of the IIAC. I studied mechanical engineering while I was there and had a great time working with the IIAC. Can everyone see my PowerPoint? Awesome. Okay. So let's get started. I am going to try and save some time at the end for questions, since I know y'all are working on an assessment right now that should have to deal with pumps a lot. But just kind of a get to know you. And I thought I'd put out a poll and see how long you've all been with the IIAC. You can either go to the address at the top online, or you can text that Moriah Henning 820. I would recommend going to the website because later I have other questions that you cannot text to. So, and I think it's easier, but up to you. Ooh, 2 semesters. This is cool. I've never used this
I love
before.
it.
Yeah. Fun to see it in real time. Really awesome.
You're seeing, by the way, Moriah, that right now our ebb and flow of the team is, it is a little more veteran than typical, which is also
that's
sort
what
of
it
a
seems
nice
like, which is really cool.
COVID, unexpected COVID positivity.
It seems like answers have stopped coming in, so I'll move on. But cool, thanks for responding, guys. That's fun to see. So getting right into it. So I'm just going to go over some pump basics. So talk about a few different types of pumps, what those might look like if you're actually on site, and then go into more calculation-based, how are you finding the energy that those pumps are using, and then I'll specifically look at a situation where you have a throttle valve and a variable frequency drive, or VFD, and how you would compare those two. And then I'll also just give you a quick overview of other things to pay attention to, and then save some time at the end for questions. So starting out, we've got centrifugal pumps, radial flow specifically. These are the most common types of pumps that I've seen in industry. They are good because they can deal with a pretty wide range of flow rates and pressures, and you are going to have a dependent relationship, which means as your flow rate changes, your pressure is going to be affected by that. So, and then in the screen, actually, let me see a second. Can you see my mouse? Yes? No? I see some yes and some no. Let's see if I can.
I see the mouse now, Moriah.
Okay, I think change it to the laser pointer. So This pump curve is very typical of what you'd see for a centrifugal pump. You've got flow rate on your x-axis and pressure on your y-axis. And so the red is your pump curve, and that is the manufacturer's standard, how the pump is going to operate. And then depending on your specific system, that is the blue curve. So that determines, so the system curve shows what your piping and friction requirements cause, and then the pump curve shows how that specific pump you have inserted into the system responds. So in this case, the blue line intersects with the red, and that's where your pump will be operating.
Right. Two really basic questions, if I could jump in on that previous slide. Can you tell the team how, just for starters, they would identify the type of pump and where they would get the curve?
Yeah, so I'm gonna, on the next slide, I have some pictures of pumps, so I will go into that. So this right here is an example of a centrifugal radial flow pump. You can tell because it has, maybe, you can tell because it has an impeller, which the rotating impeller is going to create a vacuum, pulling fluid in and pushing it out at a different pressure. And so that's, sorry, things are popping up. Can you guys see that? Oh no.
I'm able to see the pump.
Okay. Sorry, I had another screen pop up, so I was blocking. We'll just go to the next slide. Sorry, y'all. Oh, awesome. People are responding. So yeah, that is correct. That is the outlet of the pump. So it's going to come in from the right side into the center. The impeller will spin the fluid out to the top, increasing the pressure enough to send it wherever the pump needs to go. So as Julie was saying, how do you know what type of pump you're looking at? So again, this is a centrifugal radial flow because it has the impeller blades, and then it's entering from the center and being spun outwards radially. We go to the next slide. Here's several different examples of radial flow pumps. So this is the same pump we were just looking at, except closed. And then you've got one with a horizontal split case. The split casing is determined by your impeller direction. So if the impeller is this going up and down this way, and your casing splits vertically, then around the impeller, then it's that radial split case. In this case, it's perpendicular to the impeller, so you've got that horizontal split case. And then these are some multi-stage pumps, so you're not going to have just that one kind of container for the impeller. You'd have several impellers all along this multi-stage. And you see this more in pipelines, which is something that I've seen quite a bit, and where they're trying to pump further distances, so they need to get up to higher pressure. So you're going to have multiple impellers in line to get up to those higher pressures and pump further down. So maybe when you're at the U and they're trying to pump all around the campus, they might need a multi-stage pump. I'm not sure on that one, but so a different kind of pump that is not as common, but you could see is a centrifugal axial flow. So these still have that flow pressure dependence, But as you can see, they look quite different. Rather than that impeller shape, they have more of a fan-like propeller blade. You still have the inlet coming in, being spun, raising to a pressure, and going out. The pump curve for this one looks quite different. So you can see that it's kind of like got a wonky line going down rather than this just nice curve. But it's still the same thing. You've got your flow down at the bottom on the x-axis and your pressure on the y-axis. This is especially good for situations where you have high flow rates and low head pressure. And then the last type of pump that is most common is it's not most common, but it is of the three pumps we're talking about. One of the kinds you could see is the positive displacement pumps. So this one, you have an independent relationship between flow and pressure. So that means you're going to have that set flow rate, and your pressure could be anywhere along this line. It's defined by the system, and then your flow rate is going to be defined by the pump speed. So if your system's friction is changing, if you add a new pipeline to it, if you add maybe some turns in the pipe, then your pressure will go up. The flow rate will remain the same. So if you're trying to have really consistent flow rates and you don't have as high of pressure, the positive displacement pumps can be a really good option. They also have a lot of different variety in them. So when you're looking around the site and see a pump that doesn't look quite normal, maybe it's a gear pump, which is just like interlocking gears. You've got lobe pumps, which are similar but more rounded gears. A screw pump, which is kind of like a rotary screw compressor. Got the same idea where you're coming in one and building up the pressure to the outlet. So I haven't seen positive displacement pumps very much on sites. I think they're usually used for smaller flow rates, and yeah, they're not as common, but they do exist. They are out there.
The only time I've seen a gear pump was actually in a research and development lab. They were very good for like very precise measurements of liquids. Otherwise, I haven't seen anything like this either.
Yeah. So.
Right. What do you consider? What do you consider smaller flow rates?
I mean, the pumps I deal with are usually
pretty
minimum
big.
of, like thousands of GPM. So small flow rates would be anything under 50 GPM maybe. But yeah. So then to answer Julie's question of where do you find those pump curves, actually, okay, I will address that in a later slide, sorry. I do have some resources for you all that are useful in finding pump curves, and especially if you have manufacturer info on the pumps. So before we get to that, I'll jump into some common ways to calculate the energy a pump uses. So affinity laws are kind of the way, just the general way to compare different situations around pumps and fans. These apply to both. So just the basics is that your speed of your shaft is proportional to your flow rate. So if you have a motor that's at 50% speed, the flow rate will be 50% of the full capacity. And then this is useful because you can apply it to both the pressure head and power of the pump. So the power is proportional to the cube of the shaft speed or your flow rate. So if you know the power a pump is using at full speed, at its rated speed, then, and you have a flow rate that you want to reduce it to, then you could calculate the necessary speed of the pump. This also works with a changing impeller diameter. So one thing you'll sometimes see is that you can trim off around the diameter of the impeller, and that does the same thing as changing the speed. So you would just, rather than it being RPM 2 over RPM 1, it'd be diameter 2 over diameter 1. A big question with any equation is how accurate is it? I'd say the cubed rule is only good in ideal situations. In reality, your power is never quite proportional to the cube of the shaft speed or flow rate. So we often use kind of what we call a swag, or scientific wild-ass guess, with a power exponent of 2.4, 2.7 instead of that cube. All of the equations above, as I said, assume the impeller diameter is constant. If the impeller diameter is changing and you replace the speed with the impeller diameter, then you are assuming your speed is constant. And then one last note, this is good for these equations, and just the next equation we'll talk about is your brake horsepower versus actual horsepower. This equation can use either, but you have to be consistent. Brake horsepower is the power required to move your fluid, like power at the pump, and then your horsepower is the power required to move the fluid, and including accounting for inefficiencies in the motor and other attachments to the pump. So this is the power that the line sees you're actually drawing from the utility. So either one can be used in this final equation. You just have to make sure it's consistent of which one you're using. So now the question is, if we want to know what the power is at a full flow rate, how do we find that? So the answer is the pump power equation. This is, some of you have probably seen this, especially more experienced people. Pump power is just pressure times flow rate divided by your efficiency. So I have a couple with units here that I find useful. If you have your head pressure in feet, then 3960 is your constant on the bottom to convert, and if you have your pressure in psig, then 1714 is that useful constant. Oh God, they're going black. Okay, y'all can still see the presentation? Yep, okay, cool. So the other thing to note with the pump power equation is that specific gravity plays a role, and I'm actually realizing my bottom equation should not include specific gravity because your pressure would already account for that. But if you have your flow rate in, or your head in feet, then specific gravity or your density has an impact of that pressure. So if it's just water, then it's 1, and this equation is usually pretty spot on if you know your pump and motor efficiencies. If your specific gravity starts to get too far away from 1, or you have a slurry, then this equation may not be as accurate. So just something to keep in mind. And so then the pump and motor efficiency, good rules of thumb for a pump efficiency is 65%, and for a motor efficiency, either 95% or finding NEMA efficiency tables online. NEMA is your motor rating, which most of you probably have seen on the motor nameplates. But 95% if you don't know is a good guess, and 65% for the pump efficiency. But if you have the curve, then you should be able to know that pump efficiency. So now, remember this equation because we're going to take a look at how to use that with an actual curve. Maybe. Are you all seeing the notes?
Yeah, we can see the notes.
Okay.
If you go up to the left side to the display settings, it might, you can switch screen.
Looks good now.
Do you see the good now?
Yeah, just
okay.
the presentation mode.
Cool. Can you guys see the question, or is it just a blank screen? All right.
I cannot see a question right now.
Okay, that's okay. So I have an example pump curve here, which has, so that blue line is your pump curve, and then I drew a red system curve there, so that is your estimated place of where the pump is operating. And so if you guys want to try and use that pump power equation, we can talk about where you get each of the components from the curve. Oh, I think it's finally loading. There we go. We got one answer in already. So I'll give it a second. So do you guys need that equation again? Keep going.
I could see the equation again.
Okay. So it is, if I can pull it up here. Sorry, y'all. I think these polls, I like the idea, but they're making the PowerPoint very slow. Okay. So here's our equations again. So we've got our head times our flow rate times our specific gravity divided by 3960 times your pump efficiency times your motor efficiency. And I gave you a motor efficiency in that one of 95%, or 93%, I think. So go back here. Oh, no. Okay. Well, fortunately, okay. So it doesn't seem to be working, unfortunately, but we will go over it. I saw some answers of around 1250. So does anyone want? So I'll walk through what I have, and then if anyone wants to ask questions or say how they got to their answer, we can talk about that too. So This little box right here shows actually your design point, but it could be anywhere around 4,900, 4,800 feet is your head. So this black line shows you right here. And then your flow rate is this other vertical black line. So you got 583 GPM. Your specific gravity was actually right up here in the corner. And with the motor efficiency of 93%, so specific gravity is 0.42, and then divide that by your 3960, and then pump efficiency, if we just follow this line straight up to the efficiency curve, and then over to the right. And you guys can't see your faces, can you? No, that's in the way of mine. I'm sorry, I'm not used to Zoom.
What was your question, Moriah?
Your faces are all on my slide, and so I didn't know if that was blocking your view of the curve.
I can see it.
Yeah, I can see the curve.
Perfect. Okay. So if we follow this point up and then go over to the right, then our efficiency is just around 77%. And so then we take 77% pump efficiency, 93% motor efficiency, for a horsepower around 421. So if you have anywhere around there, that's about where we're looking.
I think we all did horribly.
Did anyone have thoughts or questions on why any of these numbers are the way they are?
Suddenly, a couple of our students are getting it right. I don't know how they did that.
Awesome.
Moriah, how did you eyeball such specific numbers? That's one thing that occurred to me as you were going through it.
Yeah, so I didn't actually eyeball those. If you notice, I cheated. There's a box right here that gives you the best efficiency point. So I used the values given in the best efficiency point, which is this operating point right here. So if you had anywhere close to those values in this scenario, that would be totally fine. I just used that best efficiency point, which is, as you can see, the highest point on the efficiency curve to direct my calculations.
Hey, Moriah, I don't know if you can see the chat stuff, but one point Mateo just made, which I think is a good one to touch on, is that he was assuming this is 100% water and using a specific gravity accordingly. Obviously, you're in a different, you might speak to that.
Yeah, so usually probably most of the pumps you guys would see, water is a good assumption to make. In this case, our pump curve specified up here in the right-hand corner that our fluid-specific gravity was 0.42. So it was a little more tricky because it's not water. So I think just to that point, it's important to remember to ask what the specific gravity is if you know the fluid is not water.
Right, or at least what the fluid is, right? Because oftentimes, for example, we'll see glycol mixed with water in our situations, for example.
There you go, yeah. So it's important to take into account because that can obviously wildly affect how much power the pump consumes. So, cool. So now going back to Julie's question, where can you find information that can lead you to the pump curve? So, or information you need to perform that pump power calculation. So on the left here, we've got motor efficiency, or sorry, not motor nameplate, where you can get the horsepower of the motor to compare to your pump power equation. So if you calculate something that's way outside of the motor horsepower, then you know you probably did something wrong and you should rethink that. But if you're pretty close, underneath that, it should always be less than the horsepower unless for some reason you know they're operating it at the extreme end of the pump's capacity. But other than that, it should usually be less than the motor's horsepower. You can get the nominal efficiency off of the nameplate. And then on the right, I have an example of a pump nameplate. So this one, you can see I zoomed in, it was a little hard to read, but you can get the serial number and some other nameplate information. You can get that it's a Gould pump, and then take that information and do some research if you don't already have a pump curve. Where do you do that research? So pumpflow.com is a great place to look for curves if you have the manufacturer name. They have a wide variety of pump types and manufacturers, and that you can either enter in like specific conditions that you know the pump is under, or look for a specific pump type. And then flowserve.com is its own manufacturer, but I've found it useful when just trying to look at sizings of pumps. So if I know a pump is really oversized, which I'll actually also talk about in a second, then I could go on here and try and find a way to search different pump options based on the conditions I know it should be operating at. So say the pump is designed for 500 GPM, but they actually only need like 100 GPM, then I could go on here, enter 100 GPM with a specific pressure head, and find more ideal pumps with better efficiencies and a perhaps lower motor power that could be more appropriate. Since I'm not a pump designer, I know you all are not pump designers, this isn't meant to like say they should buy this specific pump. It's more just meant to help you get an idea of what power they actually would need given specific pump conditions. So just tools that I have found useful, and you can get curves off of both of them. So now let's jump into pump control. Looks like don't have too much time left, so I will try not to spend too much time. The different types of pump control that I have often seen, the easiest one to do is just a recycled bypass line. This just means the pump is going full at its full flow rate, and somewhere downstream of the pump they have a line going back, recycling that flow rate, and anything not recycled then moves downstream. So the pump sees full power 100% of the time, even though downstream they might not get 100% of the flow rate. And then throttle valves, again, downstream of the pump, they'll have a valve that they can close off flow rate, and this pushes pressure back up. Let me see if I can mouse again.
While Moriah's doing that, I'll just chime into the U of U water distribution assessment team. You're most likely gonna, we'll see when we get to the building, but we're most likely gonna see bypass control options there.
Okay, all right, I think I got my mouse back. So throttle valve, you have this red line shows the full capacity system curve, and then as you throttle, as you close that valve and limit the flow rate going through it, that pushes the pressure higher on that pump, and so it will follow the pump curve, that blue line, until you reach the appropriate flow rate. So if you have a throttle valve, then you could say, okay, what flow rate am I operating at? I'm down here somewhere. I'm going to draw the line up to my pump curve, and that is where I'm now operating. Stop start is more common if you have multiple pumps. So you can, multiple pumps in parallel, I should say. You can start one, have that flow rate going, and then if you need more, you start up another one and to double your flow rate. So this one can be good if you have like set different like conditions of flow rate throughout the year, but it is limiting because it's either full flow rate or nothing, or double the flow rate or half the flow rate. So it doesn't give you as much variability. A 2-speed motor would also give you something similar to a VFD. So in this case, you have your system curve, you have your full flow rate operation, which is going to be out here to your right. And then as you decrease speed, then instead of following the pump curve, you follow the system curve and create a new pump curve. So you can see there's now 2 blue lines on this variable speed. So with a VFD, you could make not infinite number of pump curves, but many pump curves all along this system curve wherever you need that flow rate. With a 2-speed motor, it would be literally just what's on here. Like you have one pump curve and then you have another. So you could alternate between the two if you had very specific flow rate conditions. So then I wanted to talk about, really quick, so what if we went back to that pump curve we were looking at before and compared operation between a throttle valve and a VFD at 300 GPM. So we have our original system curve with the throttling valve, and then we have to move back along our pump curve to create a new system curve, and you end up with a much higher head pressure at the lower flow rate. Whereas with the VFD, you have that same system curve. You follow the system curve down to the flow rate you want, and then you've created your new pump curve with a much lower head pressure and lower flow rate. So if we use our pump power equation to compare those 2 different scenarios, you can see that our throttling valve has a much higher power consumption than our VFD. So, and then just some last recommendations besides VFDs.
Hey, Moriah, before you go past that, I want to ask one topic that comes up often is, do we include demand and use savings with VFDs or not? Can you comment on that really quick?
Yeah, I think it would depend on the system and whether a VFD is being used to control a lower flow rate all the time or just some of the time. If it's just some of the time, then I would say demand shouldn't be included. If it's a lower flow rate most of the time, then I would say yes, include demand. Also, sometimes what we do is we use an average demand, which is kind of wonky because it doesn't represent the demand they see on their bill each month, but rather saying on average you'll see a lower demand than you do right now, and then use savings off of that. Yeah. So back to our recommendations. Oh no, I'm not saving time. So many pumps are oversized just due to the way manufacturers install pumps. So if you see a pump that's operating way to the left of its curve, so at a lower flow rate than it's designed for, it could be a good candidate to install a totally different pump with a smaller motor. If you have multiple pumps in a system, sometimes you'll see a bunch of pumps running at part load, and it's always more efficient to run a pump, just one pump at full load, than it is to run multiple pumps at part load, if that is a possibility. If a pump already has a VFD on it, but they have a throttling valve that they're using, you can open up that valve and have the VFD slow down the speed. So that's just improving control logic on equipment they already have, or the customer, or whoever already has. Piping is something to pay attention to when you're looking at your upstream and downstream of your pump. If the pipe is too small, or you have kind of ridiculous piping that's going all over the plant to get to, you know, something like 100 feet away, then you could say, why don't you just add one pipeline just directly to the next tank or whatever it's going to, or increase that pipe size to reduce the friction losses. So, and then the last one, installing a throttling valve might seem counterintuitive based on what we just talked about with the VFD versus throttling valve, but it can be a cheaper option, and it still does decrease your power consumption if you are trying to control to a lower flow rate rather than just using a recycling line. So that can still be
I'll
an
jump
option.
in and say this is a great roadmap for the U of U team. These are options we should be looking at. Also, for any future water distribution assessments that we do, those are all good things to look for.
Awesome. Yeah, so this is my last slide. One thing I didn't really get into in this presentation at all is configuration of pumps. It's very important, and so I kind of included a couple pictures of curves with series or parallel operations. Some of you are asking about costing. A lot of the costing we do is based on quotes, which I know is not always possible for y'all to get, but vfds.com is helpful for cost estimates for low voltage VFDs and motors. And then last note, if you're wondering how we calculate our incentives, it's pretty simple for capital projects. It's the minimum of those three options, either 15 cents per kilowatt hour saved, 70% of the project cost, or however much money puts the project at a 1-year payback. If it is an energy management project, which would be some sort of shutoff, a tune-up of system controls, a set point change, something that doesn't cost very much money for the customer, then it's 2 cents per kilowatt hour saved. So I know I'm at time. I'm sorry about that, y'all. But does anyone have any questions?
It's actually perfect timing, Moriah. You kind of nailed it compared to our normal speakers, so awesome. Obviously, if people need to go, our class time is up now, but sounds like Moriah is willing to hang out with some questions for a little bit. You're also welcome to stay and take the opportunity to ask her any questions about pumps while it's on your mind.
I gotta run, but thanks, Moriah. That was awesome. Are you gonna give us these slides for reference? Because that would be awesome.
Yes, I can do that.
Okay, sweet.
Also,
thanks.
James recorded.
Perfect. Thanks, Moriah.
Yeah, thanks, James. Nice to see you.
Thank you.
Moriah, there seems like there might be a question in the chat. Are you able to access that?
Let's see, chat. Yes. I'm from Mateo. Is that the last one, or? Oh yeah, pump setup can be seen in similar ways to voltage and current for series and parallel. That's exactly right. Whoever said that.
Well, I'll jump in with a question while everyone's thinking. Just knowing your new context with pipelines and so forth, Moriah, what do you, so the vfds.com is a great resource for costing. Thank you for that. What do you consider these days to be low voltage?
So low voltage would be anything below like 1,000 volts. So, and then medium voltage, medium voltage would be like 2,000, I guess maybe below 2,000. So like 2,000 volts and to around 12,000 volts would be medium voltage, and then above 12,000 would be high voltage.
You guys can get a good context of the situation Moriah is dealing with these days. Some people might call low voltage to be like control voltage, which is 20 volts. So it's a good clarification.
Yeah, thank you for that. I should say that your VFDs get much more complicated once you get above a certain voltage and much more expensive as well. So people are less interested in doing that, but they still do, and they still work.
Moriah, I've got a question for you, not about pumps so much. Can you tell us how much your current job is similar to working for the IIAC? How much does that experience cross over into the professional world?
Yeah, I think the engineering part of it was probably the most helpful and most crossover that I saw. A lot of the work you guys do, looking at assessments or looking at your assessment recommendations, is stuff that I do as well. I think the parts where it doesn't cross over is that we have to help the customers implement the project. Since that ISC is just mostly ideas, you kind of present and leave it, but we have to make sure we're presenting projects that customers can afford and are interested in doing. And so like that kind of adds like a whole nother component to it.
Do you like that component of it?
I do and I don't. It makes it harder for sure. Because sometimes you just want to be like, I have all these ideas, but you have to tone it back and be like, well, what's realistic? So.
Do you typically do some of the design work, or do you just try to do matchmaking and partner them up with a design build vendor?
No, we don't do any of the design work. We leave it to them to find a vendor. We do work with, especially like for VFDs and stuff like that, we work with a lot of vendors, and so we can recommend that to them. But in the end, it's up to them. And for stuff like compressed air, they often have a vendor that they are already working with and like have bought all their compressors from. So they usually just will like keep working with them. Yeah, so it really depends on the project.
Awesome, thank you. Thank you so much for today's presentation. That was really informative and cool to have you back.
Yeah, thanks for having me.
Any other questions, team, class? Otherwise, Mariah's got to get back to billing her hours.
Well, Moriah, if you don't mind, I actually have 2 quick questions for you.
Yeah, for sure.
Yeah, could you go back to the page where you were going over the pump affinity laws?
Let's see.
Hopefully one of my questions you can answer on the way there. Yeah, okay. So you said that you don't always use an exponent of 3. You tend to use 2.4 or 2.7. And I was just wondering which number you would recommend using for a more conservative estimate for our purposes.
The lower you go, the more conservative it is. So 2.4 would be more conservative.
Okay.
Yeah.
Cool. That was easy. Second question, this one's a little bit more silly. Why do they call it brake horsepower?
You know, I don't know the answer to that one. Does anyone else?
I don't remember, but Conrad's in fluids right now. Who's your fluids professor, Conrad?
Professor McLennan.
Ask him and remind the rest of us.
All right, I'll fill in the group.
We still have time to have a question,
too. This was a great presentation.
Awesome, thanks, Conrad. Did someone else say they has a question?
Yeah. How often do you have to like consider friction loss, like in your calculations? And if it's often, like, what are like some telltale signs that we should consider it as well?
That's a good question. Typically, we don't. So the pump curve itself takes into account your friction losses. That's what the system curve is. So, so if you know what the system curve and the pump curve looks like, then you don't have to necessarily calculate those friction losses. However, if you're looking at piping changes, that's when I would start taking into account friction. And then there's some common equations online, and also I think maybe some tables of kind of just friction factors in general, but pipe size, pipe schedule, pipe length and diameter, all of those fluids, things you have to take into account. So yeah, I think if you're just looking at the pump itself, the pump curve should be sufficient. If you're diving into more of the piping stuff, then that's when you have to start paying more attention to your friction losses.
Thank you.
Mm-hmm.
Going once, group? Any more questions for Moriah? Sounds like crickets to me, Moriah, which means everybody is happily satisfied and has no more pump questions and are ready to be experts.
All right. Well,
Can we give Moriah a big hand virtually or physically?
oh, thanks.
Thanks, Moriah. That was excellent.
Yeah, thanks for having me. Sorry for some of the technical difficulties. It wasn't as smooth as I wanted it to be.
That is what every single professor is dealing with that right now with Zoom, and so totally understandable.
Thanks, Moriah.
Awesome. Well, yeah, I'll let y'all go.